Alright, this is lab 2. This is the lines of charge lab, in which we create a new computational model and visualization of lines of charge tape. So the goals of this were to build on some of the results that we got from lab 1. We, in that lab, used charge tape and measured some things about it in a few different configurations. We had some estimates for the amount of charge on the tape, and it was all under a specific point charge model for the tape, wherein we assumed that all of the charge is equivalent to being at one point for a given tape. So we are making a new model in this lab, computationally, that resembles a line charge, a string of point charges, and we're comparing that to see how much the required charge estimate differs using this model from the analytic point charge model. So these are some of the values that we got from the previous lab. This is what we're working with, and things about the system, and some of the assumptions that we're carrying over, which are namely that the two charges have an equal charge, the two tapes have an equal charge, and they're evenly distributed along the tape. Also, things aren't moving very much, so we're ignoring air resistance, and we are also using a finite, discretized version of our line model in which it's several point charges instead of a continuous distribution. So, in our code, we start with some of these physical constants, the mass taken from the slide above, and some charge, which we knew from the previous lab, as well as g. We have to build a helper function to create the electric field definition at a given point, and this specific implementation uses the origin as a source. It's only true if the source of the charge is at the origin. We have another helper function here, which just helps define the line of charge, these line of point charges that represent the tape. And this is a visualization of the tape objects once they're created. You can see it's just a simple line of positive and negative tapes. So now we actually calculate the electric field given by each point from the sum of all of the other influences from the points below. This is what the code for that looks like. It's a pretty simple loop, and then in the output we get to draw arrows that represent the gravitational force and the electric force on this top tape. Our system was the top tape, and we were observing the condition in which gravitational and electrical forces are balanced. In our simulation, given the values that we measured in the previous run, we noticed that there is a slight discrepancy between the electrical force calculated and the gravitational force, but they're on the same order of magnitude. They look pretty similar. It matches, to some extent, the results of our point charge model, in which these two forces canceled out. So now we're going to estimate the required charge to achieve this equilibrium using our new line charge model. This is what the math looks like here. Calculating everything, we get something on the order of 4.2 times 10 to the negative 8 coulombs is our estimated charge on the line to maintain this equilibrium. And taking from the previous lab, the point charge estimate was kind of close. It was 4.7 times 10 to the 9 coulombs. So it was off by about a factor of 9. The ratio is exactly 8.9. And in the previous lab, we also used this quantity to calculate the number of electrons that are contributing to this charge. And similarly, these are off by around the same factor, but not too bad. Okay, we're going to go back to some of the assumptions that we used to create this model. We're ignoring air resistance. We are treating the long tape as a point charge, or we were treating it as a point charge, now we're not. This is the main difference between lab 1 and 2. And we are assuming that the two tapes have equal charge, and they're evenly distributed along the tape length. There's no homogeneity in the charge distribution. And then there's the finite discretization thing that we talked about. We also ignored the tape width and edge effect. The tape is just a single one-dimensional thing in this model, and things like the humidity of the room that affects dust attraction, or potential accidental discharges of the tape that might undermine the assumptions of equal charge on each tape. Alright, of course there were some limitations. There were all of these experimental error things like I was just talking about, modeling limitations like the finite discretization. And if we were to do this again in the future, we could pretty easily improve things by just increasing the number n. N was the number of point charges that represented this line. More of those represents a more continuous line. We could model the tape as a 2D strip, so we don't have to ignore width, which would add another dimension of direction of charge from the bottom tape to the top tape for each point on the top tape. And there are other environmental effects, like the humidity, that we may need to model in the future. So, in conclusion, the distributed line charge model yields this as the total charge on the tape, and the point charge underestimates that by about a factor of 9. We say underestimates because we assume the the line charge model to be more accurate than the point charge model. In conclusion, just the thematic conclusion of this is that the geometry and the distribution of the charges matter, because we expect the line charge model to be more realistic for these finite length tapes we're working with. That's all. Thank you.